Yes, students, let me know. What is an ideal gas, students? Anybody? You heard of this word called ideal gas?
Pressure and temperature is constant, sir.
No, dear, no. Okay, so ideal gas is one which obeys certain laws. Okay. Yes, good, Darwin. Fuzail, you need to get on to your video again. Galson, it's already time. Huh? You've asked for a couple of minutes. You have to be on. Good, Galson. Good. Amo, again, you should manage your breakfast, everything earlier. Okay. You will have to be on video shortly. Kritvik, Hemant, you have to be on video. I don't want to manage this. Okay, going forward, please see that you are self-managed, right? I've been clearly given instruction from principal that if there's anybody not on video in the online class, they have to be removed from the online session. Okay, it's a clear instruction given from principal, okay, and management. We'll strictly abide by that. Okay, no excuses for anybody. Yeah. Yes, Ritvik. Good, Ritvik. Yes, good. I think you can log off from the other one. Yeah, okay, good. Yes, Hemant, good. Okay. Amo, get on video soon. Okay. Right. Let's begin, students. So now let me talk about what is a ideal. Anybody can come up with what is an ideal gas. Okay. Ideal gas is a gas which is said to obey certain conditions. Okay. There are about 4 conditions. I'm going to summarize all of them and put it into one. Okay. Are you able to see my screen, students?
Yes, sir.
Yes, very good. So there is something called as an ideal gas equation. So can anybody tell me what is ideal gas equation? In the previous syllabus, we used to have what is called as states of matter. But that chapter has been removed from the present chemistry syllabus. However, you are going to learn it in detail in physics under the chapter called gas laws, or in other words, you're going to have kinetic theory of gases, then you have thermodynamics. All these topics are going to be dealt in depth. But as far as thermochemistry is concerned, just an introduction of these topics, and then most important is your chemical energetics. We'll be talking about that. That means the energy change involved in chemical reactions. That's what is extremely important in chemistry. Okay. So has anybody learned about this equation in a lower class? EV is equal to nRT? No. I'll just explain the terms, guys. So P refers to pressure of an ideal gas. V refers to the volume occupied by the gas. N refers to the number of moles. R is a constant of proportionality called universal gas constant. And T refers to the temperature. All right. P refers to pressure occupied by the gas. V refers to volume occupied by the gas. N refers to the number of moles of the gas present. R is something called as molar gas constant. T is called the absolute temperature measured in Kelvin, right? Please take down this equation. Okay, now I'm going to explain a couple of processes for you guys. We'll do that in detail in your physics, but then I'm just going to touch upon that. There are different types of process. One of the processes is called isothermal process. Any idea what is an isothermal process, students? Therm refers to temperature. Iso, same. So process which happens at constant temperature is what we call as isothermal process. Okay. Let me give you an example. Let's say I have a vessel. which is connected to a piston, right? And there is some gas inside, okay? Now what I'm going to do is, I'm going to apply pressure here, okay? So when I apply pressure, what do you think will happen to the piston? Or basically, I'm going to push the piston down. Is that clear? So when I'm pushing the piston down, what do you think is happening to the gases which are inside, students?
A volume decreases.
Fantastic. Yes, Enoch. So I'm increasing my pressure, increasing the pressure that I'm applying. So which results in a decrease in the volume of the gas occupied, correct? So what is happening now? Now my piston is not at the position which I've drawn in the case 1. What has happened is piston has gone down. Now the same amount of gas is there. The number of moles has not changed, but then the volume has decreased, isn't it? Now, there are 2 ways in which I can do this process, correct? The same amount of gases are occupying lesser volume, correct? Okay. Is this clear? The first step is clear what I'm doing, right? Now, this process I could have done it in 2 possible ways. One way is I do it really fast. This movement of the piston is done very fast, right? Then such a process is going to be called as adiabatic process. That's a different one. Okay, second. But if I do this process very, very slow, right? I move this piston very, very slow and bring about compression of the gas. Then this process is called what? Isothermal process. What happens here is when I do it very fast, what happens is the gas compresses. And compression always, can you tell me what will happen when a gas is compressed or when pressure is applied? What do you think will happen, guys? What will happen to temperature? With logic, you can answer. Let's say you are in a big marriage hall, 1 person, you're in a big hall. What's going to be the temperature, right? What's going to happen to the temperature? Or let's say 100 people are there in a big marriage hall, which can accommodate 500. What will happen to the temperature? Let's say, they are into a smaller hall. Let's say something like a seminar hall 2. What is going to happen to the temperature? Now I'm going to pack them inside a classroom. What is going to be happening to the temperature? Can you just tell me, guys, with your logic?
Temperature increases, sir.
Absolutely. So whenever there is compression, it increases the temperature. Makes sense, right? Okay. So now what will happen is, if I'm going to compress the gas fast, there is a increase in temperature, correct? And what can you say about the amount of heat energy that is generated? Is it going to increase or not? Or in other words, let me tell you this way. So the increase in temperature, what happens is, if you do this process very fast, there is no time for it to transfer to the surroundings. Is that clear? So, a couple of terms you might have listened to when the teacher is talking or teaching thermodynamics. So here, system and surroundings. So, the gas which is under observation, right? We call that as what? Your system, right? And everything else which is outside world, right? So that's called as what? The outside world is called surroundings, okay? Okay, there are different types of system. Again, it will be done in detail in your physics, but at least a couple of them, like, open system, closed system, you can just understand isolated system. These 3 types of systems. What is an isolated system? Isolated system is one in which there can be no exchange of matter as well as energy from the system to surroundings or from surroundings to system. It's an isolated system. All right. Second one is what? A closed system. When I say closed system, right? For example, what we're talking here is a closed system, which means matter cannot be transferred, which means your gas molecules which are here inside the piston or inside the, inside your system, it cannot escape to the surroundings. Is that clear? That's called as a closed system. Am I right, students? Those of you who already know it, yeah. But however, energy transfer is possible, which means, If there is a heat generated, there is a possibility of that heat spreading to the surroundings, right? Vice versa also. That means, the energy from outside can also enter into the system, but matter cannot be exchanged. Is that clear? Then we have something called as open system where both is possible. Is that clear? Okay. Now what we're talking about in our example here is a closed system, which means what is possible, what is not possible. Could you tell me, students? Energy
Transfer of energy.
Yeah, tell me,
Transfer of energy is possible, but transfer of matter is not possible.
Excellent, excellent. Perfect. That's it. Okay. So transfer of energy is possible. Okay. Now what happens is I'm going to press the piston very fast. When I press the piston very fast, this compression happens very quickly, right? When this compression happens very quickly, there is a sudden rise in temperature. All right. Now, if you allowed enough time, then what would have happened is this rise in temperature. What would have happened is the excess heat that is generated will be dissipated to the surroundings, and temperature would have remained constant. Okay. I repeat once again. If I had done this process very, very slowly, this compression process, temperature would try to rise, but immediately that energy is transmitted to the surroundings, so temperature will be remaining constant if I do it slowly. But the moment I do it very fast, what happens is temperature increase is sudden, and the heat energy that has increased is also sudden, and there is not enough time for this heat energy to be transmitted to the surroundings in this process. Is that clear? It's a fast process. That's called as a adiabatic process. When I'm doing it fast, it is adiabatic. Temperature change is so fast. Because of that, heat energy is generated within the system, and there is no time for it to get transferred to the surroundings. Is that clear? So what happens is, it is absorbed by the molecules. When it cannot go outright, it has to be absorbed by the gas molecules which are there. So energy of the gas molecules increases. So when energy of the gas molecules increases, it increases in the form of kinetic energy. Now these molecules are going to travel faster. They're going to have increased velocity. All this what I spoke to you till now is what process? Yes, Levin, you're on mute.
Adiabatic, sir.
Exactly. Adiabatic process. That means, it's a fast process. I'm doing this compression very quickly so that the heat is generated, temperature is raised, but there is no chance for this heat to go out to the surroundings. This increase in heat is converted into kinetic energy. It's absorbed by the molecules. It increases the internal energy of the system. We say it increases the internal energy of the system, which means every molecule, what earlier kinetic energy was, now it's going to be higher than that, and which results in molecules moving faster. Okay, guys, this is called adiabatic process. You have certain equations for that. We'll discuss all of that in physics. Okay. Now coming to isothermal process. So what is isothermal process? First thing is it's a slow process. Okay. So I'm compressing this, I'm pressing this piston very, very slowly. So what is happening is there is a rise in temperature. There is an apparent rise in temperature. There is an apparent rise in energy. But what happens as this energy increases? Because there is time, what will happen to this energy which is an increase which has come because of compression? What will happen to this energy? Come on, guys, quick. It will have time to get out to the surroundings. So what will happen, students? When this energy goes out into the surroundings, the internal energy of the system, will it change or not? Hello?
It will decrease. Decrease.
Listen now, listen. See here, originally, let's say the energy was Q, okay? Now, because of this compression process, it became Q plus delta Q. But what happened to this delta Q? It got dissipated. So what is it going to remain now?
Remains
Remain Q itself. Therefore, there is no change in the heat energy, isn't it? Or in other words, there is no change in the internal energy of the system. So do gas molecules gain more kinetic energy, or do they have the same kinetic energy as before?
Same kinetic energy.
Same kinetic energy, isn't it? Because the excess heat that is generated is dissipated to the surroundings. So there is no change in the kinetic energy of the molecules, or in other words, there is no change in the internal energy of the system. So internal energy we represent by delta U. So change in internal energy is 0. What else is 0, guys? Is there any change in temperature inside the system? No. Why? Because you're doing the process slowly. Any apparent increase in temperature is going to be dissipated to the surroundings. Is it clear? Therefore, there is no change in temperature as well. Okay. Now, is there some work done, students? If you have to move the piston down, there is some work done. Yes or no? And this amount of work done is given by change here. You know that what is work done? You're applying a force and there is a change in displacement, isn't it, guys? Earlier, let's say this height was h or h1. Now this height is h2. So what is the displacement which has happened on the piston? h1 minus h2, yes or no? Yes or no, guys? The distance has changed, correct? So it is force into displacement. But what is your force into displacement? Come on. In terms of pressure, because we're applying pressure, right? So what do? I divide by area, multiply by area, okay? So what is force by area?
Pressure.
Pressure. What is area into displacement, or what is area into length? It's a cylindrical
volume.
Come on.
Volume.
Absolutely. So P into V, right? In fact, what is changing here? Pressure is not changing. You're applying the same force on the same area. What is changing is the displacement is changing. Hence, what is changing? Volume is changing. So your work done on the system is P into delta V. All right? Pressure into change in volume. Okay, this is one thing which you need to know. Okay. More details. Let's say we discuss about adiabatic process. All that we'll see in physics. Okay. Now next, few other things that you can understand is if the process happens at constant pressure, it's called as an isobaric process. If it happens at constant volume, then it is called isochoric process, and so on. Okay. So we will just at this point limit ourselves to what is important in chemistry. Okay. Fine, guys. So this is clear to you. So the amount of work done in moving the piston down is what? P into delta V. Is that clear? Pressure into change in volume. Excellent. Now next. Yes, ma'am. Good. I'm okay. Everybody's good. Now, let's now look into first law of thermodynamics. Okay. And then we'll move on to chemical energetics. So any doubts in what I have discussed so far? Anybody has any question? Please feel free to clarify. Get it clarified. If there are no questions, then I'll ask you a question. Okay. Have you taken down? Can we move on? Okay. Jeevan, now answer this question, Jeevan. Okay, I have some gas molecules inside occupying a particular volume V1. Now let's say I'm doing one thing, okay? I'm supplying heat from outside, okay? I'm supplying heat from outside. Okay? Now, what do you think will happen? What are the things that will happen, Jeevan? Can you think Can you tell me?
Heat is increasing, sir.
So this is my
this-
system. So from outside, I'm supplying heat. So what will happen is my gas molecules inside will experience an increase of heat, correct? Yes. So what it will try to do?
reduce the pressure. It will increase the pressure of piston. I mean,
Good.
will
Okay.
oppose the
Sorry, ma. Again, please.
will oppose the piston.
Yes. Very good. Very good. Good. Okay. Super. So what will happen to the piston?
Piston goes up.
Very good. Excellent. Excellent. Piston will go up. Until what point will it go up?
Pressure becomes it becomes equilibrium.
Very good. Excellent answer. Excellent answer. Okay. Very good. Now listen, students, everybody. So I'm supplying some quantity of heat here. Okay. Now what is going to happen is the piston is going to move up. The molecules which are here, Ajivan, are they going to gain some energy?
Heat energy, sir.
Yes, they'll gain heat energy. And because of that, how will it reflect on the molecules? Yeah, Evelyn, you're on mute. Were you trying to say something? Okay. Yes, Vinay, you're trying to say something? Okay, good. So, heat energy will increase or not? It will increase, or in other words, the internal energy, so it will reflect as increase in internal energy. That will also happen. And when sufficient amount of heat is given, it will also result in the moving of piston up. Very good. In order to maintain pressure constant. Very good. So pressure will be in equilibrium, which means the pressure outside the piston will be same as the pressure inside the piston. Till that point, this piston will move up. Very good. So what is happening to volume, Jeevan?
Volume is increasing.
Volume is increasing, correct. Pressure is remaining?
Constant.
Constant, correct. Is there some work done on the system?
Yes.
Yes, and what is that work done? Can you tell me what it would be? You've already seen before. What is the expression for work done, isn't it?
P into delta V.
Exactly. Correct, ma? Good. So this difference in height, right? Whatever it is. It's earlier where the person was here. Now it has gone up, let's say. So the same gas molecules are occupying more volume now, correct? So volume has increased. Pressure it's performed at constant pressure, right? Which means you're not you're not sealing this, right? This is free to move. So this moves so that the pressure comes in equilibrium, which means the pressure outside is equal to the pressure inside, right? This is when we call it is in equilibrium, correct? So your volume has increased. So the work done on the system by the heat that is provided is, can you tell me the expression for that, Jeevan?
P into delta V.
Very good. P into delta V. And in addition to that, what else has happened to the molecules?
It gained internal energy.
Very good. So internal energy also has increased now. So delta U represents change in energy. All because of what? These both the things happen because of what?
Because of heat.
Yes, the heat that was supplied, right? So the heat that is supplied, part of it is converted into increasing the kinetic energy, increasing the energy of the system, and remaining is done as what? Work. Is that clear, students? And remember, I have given this equation from the perspective of physics. There's a slight difference in the way the sign conventions are I will just make it clear. It's a very simple stuff. See, in physics, always we want the system to do work, correct or not? Yes or no? So, when our system does work, then we take that work done as positive in case of physics. Okay. So, the piston has moved up means what? Volume has increased, work done is positive, correct or not? Work has been done on the system. Or sorry, by the system, right? So, you take this work as positive in physics. Opposite in chemistry, you take it as negative. Okay. That's not a very, very important stuff. Don't worry about that. Don't break your head on that. Just understand the concept. Then the sign convention you can always figure out. Okay, no big deal. Suppose I'm applying pressure, like the previous example. If I'm applying the pressure, the piston is going down. Then what is happening? Work is done on the system, right? When work is done on the system, in physics, we take it as negative because you're doing some work means you're spending some energy. Correct or not? So it is. You're doing work on the system. System is not doing work, right? So you take it as negative in physics, but in chemistry, you would take that sign as positive. So that's fine for you guys. Don't worry about, don't worry too much about it. Okay. So what is important is getting the logic right. So quantity of heat that you supply, part of it is converted into increasing the kinetic energy of the molecules and in turn the internal energy of the system. Remaining part is converted into or some useful work. Is that clear, students? Yeah, so this is your first law of thermodynamics. Quantity of heat is equal to change in internal energy plus the amount of work done. Okay, fine. So now these two are the important aspects as far as the thermodynamics part of your chemistry is concerned. Rest of thermodynamics part we learn in detail in 2 chapters, right? One is based on gases, kinetic theory of gases. Second thing is the thermodynamics. In detail, every single process we will learn it with graphs and everything. Okay, so right now we'll just understand this. With this knowledge, let's attempt a couple of questions and come back and get into energetics. Let's look at the first question, students. Okay. An ideal gas expands from 10 power minus 3 meter cube to 10 power minus 2 meter cube at 300 Kelvin against a constant pressure of 10 power 5 Newton per meter square. What is going to be the work done? Okay. So what is work done, students? Come on, quick.
Delta V.
Yeah, P into delta, right? Change in volume. What is your pressure? Pressure is 10 power 5 Newton per meter squared. And change in volume. Come on, tell me. Which is bigger, 10 power minus 3 or 10 power minus 2? Quick. 10 power minus 3 is smaller, isn't it? Okay. So change in volume is 10 power minus 2 minus 10 power minus 3. So that's going to be 10 power 5 into 1 upon 100 divided by 1 upon 1000. So that's 10 power 5 into LCM is 1000. So 10 minus 1 is 9. 9 by 1000. Correct? So it is 900 joules of energy. Or in other words, I can write this as 0.9 kilojoules. So which option is correct, students?
Option C, sir.
Option C. Is that clear to you? Please take it down. Can we move on to the next question? Any questions in this? Sadiq, turn on your video. Are you there? Yeah. Shall we proceed, students? Shall we move on to the next question? Are you ready? Aditya, ready?
Yes, sir.
Yeah. Video on. Fusail, video on. there's anything important, any emergency, you'll have to message me on the, either you can put it on the chat box or message. Okay. Now let's move on to the next question, students. Okay. Come on, this you must be telling me on your own. Second question. The work done by a system is 8 joule. When 40 joule of heat is supplied to it, what is increasing the internal energy of the system? Like this, you should tell me. How do you answer this question? Based on first law of thermodynamics, isn't it? Yeah, who is that?
Me, sir.
What is the answer, Enoch?
32.
Absolutely, no doubt about it. Right? I hope you understand, right? So what has happened now? You supplied the heat. Some amount of heat is used up in increasing the internal energy of the molecules. And the rest is used up for doing work. So quantity of heat supplied is used up in increasing the internal energy of the system plus doing work. That's it, guys. What is the quantity of heat supplied? 40 I have supplied. What is the work done by the system? 8 joules. This I don't know, let it be X. So what is my X, students? 40 minus 8, 32 joules. No brainer, right? Good, very good. Is it common sense? Makes sense? Any questions? Okay, good. Just give me a second, students. Okay, students. Now let's move on. Let's move on to next concept. So the best way of understanding the second part of your thermodynamics, actually it is not, still here is thermodynamics. Beyond it, it's called thermochemistry or chemical energetics. Okay. Very simple. We have heard about reactions, right? We have heard about reactions which are called endothermic. We have heard about reactions which are called exothermic, right? So can you tell me what is an endothermic reaction, students?
Energy is absorbed, sir.
Yes, for a reaction to take place, energy is absorbed. That is a endothermic reaction. And what is an exothermic reaction?
Energy is liberated.
Energy is liberated. So when a reaction is exothermic, right? 2-3 points I want you to keep in mind. So here, first of all, you should understand it's a natural process. An exothermic reaction is a natural process. Why do I say that? Because you know that why do atoms combine to form molecules, or why do molecules combine to form another set of products, right? Could you tell me?
To attain stability.
Attain stability. In terms of energy, can you speak, Enoch, or anybody else?
Inversely proportional.
To attain.
Or in other words,
To
can you talk about
minimize
the
their overall energy.
Evelyn, could you come again, Evelyn?
To minimize their overall energy.
Yes, Evelyn. So can I tell, in a natural process, what is happening is reactants combine and products are formed. If you compare the energies, which will have more energy, which will have less energy? Could you tell me?
Atoms will have more energy.
Or in other words, now we talk in terms of reactants and products. Can you tell me?
Reactants.
Reactants will have
more energy.
More energy, and products will have
Less energy.
Less energy. Which is more stable?
Products.
Product is more stable. That's why the products are formed. So products have less energy, reactants have more energy, means has it liberated energy, has it absorbed energy?
Liberated energy.
Liberated, isn't it? So it's an exothermic reaction, correct? So now we talk about heat change of a reaction. And that heat change is given a word called enthalpy. Okay. So there is a word called enthalpy of a reaction, which is nothing but heat change in a reaction. That's it. So if reactants combine to give you products, let's say the products are having an energy, heat energy H2. Let's say the reactants were having a heat energy of H1. Then H2 minus H1, what is it? The heat energy of the products minus the heat of the reactants gives you what? Change in energy, correct? This we call as enthalpy. Okay, enthalpy of the reaction. Now tell me, if it is an endothermic reaction, what will be delta H? Will it be positive or negative? If it's exothermic, what is going to be delta H? Tell me, ma'am.
For delta H, endothermic will be positive, sir.
Why?
H2
H2 and H1, what I have told you. First start with exothermic. Exothermic is a natural process, which means reactants combine to form products by release of energy, correct? So when energy is released, what is the energy of the product? Tell me, Jerome. In comparison with that of the reactant.
it will be positive, sir.
No. Let's go step by step, ma'am. I'm asking you, see here, listen. I'm talking about exothermic reaction. Exothermic reaction means energy is released, correct? Reactants have higher energy or products have higher energy in an exothermic reaction? I told you it's a natural process, right? Yes, Evelyn, tell me.
Products will have more energy.
You didn't listen to what conversations we had before. Evelyn, come on, clarify it.
So reactants will have more energy.
Yeah, in a natural process, reactants are less stable, products are more stable, reactions have more energy, products have less energy. So H2 will be less, H1 will be more in a natural process, which is an exothermic reaction, which means energy is liberated. So what happens is H2 minus H1 is negative, isn't it? Because H2 is a smaller value, H1 is a greater value. So this is negative. So for an exothermic reaction, delta H is negative. And the reason is, of course, you told Jerome that exothermic it is negative, but I wanted to ensure, you know why it is so. Okay. Now, suppose, let's say I have reactants, I want to convert them into products, but maybe for some commercial purpose. But this time, it's not a natural process for the products to be formed. I may have to supply some heat, yes or no? I may have to somehow make that reaction possible. All right. So which means I'm going against the nature, which means I have to supply some heat, correct, for the reaction to happen. Which means products will have more energy or reactants will have more energy. Tell me, guys. Come on, ma. Initially, you had 100 rupees. Now I give another 100 rupees to you. Are you having more money or not now? Yes, or no? Reactants add some energy. Now I'm heating them. I'm giving them more energy. So don't you think the products are going to have more energy now? What they already had plus what I'm giving. Yes or no? Yes. So if the reactants energy was H1 and the products energy was H2, which is greater now? Tell me, students. Yeah.
Products.
Tell me, Jerome.
Products, sir.
Yeah, H2 is greater than H1. So what is my delta H now? Delta H is change in energy, right? H2 minus H1, what will it be now?
Positive.
Exactly. And what kind of a reaction is this when I supply the energy to the system?
Endothermic.
Exactly. So for an endothermic reaction, delta H will be what?
A positive.
Exactly. Okay, fine, good. Now, usually use the word enthalpy. Then what is important is if I say enthalpy of formation of a particular compound, right? So we have under enthalpy of a reaction, enthalpy, we have multiple subdivisions. It's not, you can go through it on your own. Only one thing which is common, I will tell you. And anyways, I will, you will have the recordings ready for, it will be as a playlist. So you can watch one after the other. Those of you who are not part of that detailed class on thermodynamics, that will also help you guys. Okay. But this is the fundamental. Okay. With this knowledge plus a few numericals, you will be done. You don't have to worry too much about it. Okay. So let me tell you, usually when we use the term enthalpy, right? So let's say I have an equation, let's say formation of ammonia. Let's say nitrogen combines with hydrogen to give you ammonia, right? So let's say we talk about ammonia formation. So whenever I talk about enthalpy of this reaction or enthalpy of formation of ammonia, it is understood that I always, if I give you a number, let's say enthalpy of formation of ammonia is X joules, if I say, then the enthalpy of this reaction is not in X joules. It is the enthalpy of formation of, even though I don't explicitly say, it means when I say enthalpy of formation of ammonia, it means the heat energy involved in formation of 1 mole of ammonia. That 1 mole is not specified when I simply say enthalpy of formation of ammonia, but it is implicitly understood. Okay. So suppose, now I'll give you one question, common sense question. Okay. Let's say I tell you enthalpy of formation of ammonia is X joules. Tell me the enthalpy of this reaction. Anybody? I repeat my question. Enthalpy of formation of ammonia. That means the heat change involved in formation of, I won't give the complete definition. Or let me give you. The heat change involved in formation of 1 mole of ammonia is X joules. That's called as enthalpy of formation of ammonia. Then what is the enthalpy of this reaction? Tell me. Come on, give me an answer, guys. Even if you're wrong, it's absolutely fine. Go ahead. Sadiq, tell me. We have a silent class here. Huh? Come on, Enoch, tell me, ma. One chocolate I get for you, 5 rupees. Now I'm asking for 2 chocolates. How much? Come on, unmute. Tell me. 1 chocolate is 5 rupees. 2 chocolates.
Exothermic.
10 rupees, right? What did you say now?
Exothermic.
No, I did not. That was not the question, dear.
The enthalpy.
The question is, listen to it again. Enthalpy of formation of ammonia is X joules, X, not EX. Okay, I think. X joules. Then what is the enthalpy of the given reaction? This reaction. From the stoichiometric equation, don't you get that this is formation of how many moles, ma?
2 moles, sir.
2 moles.
Moles of
I gave you
ammonia.
for 1 mole. 1 mole it is X joule. What is it for 2 moles?
2x.
Huh?
Joules.
2x joules, correct or not?
Joules.
That's all. One sec, students. Yes, students. Okay, fine. So we have different types of enthalpies of reaction. So let me tell you one thing. Actually, when we discuss the questions, you will understand it best. Okay. So when I say enthalpy of a reaction, for example, let's say A moles of A combines with B moles of B, giving C moles of C and D moles of capital D. Okay. Am I audible, students? Everybody?
Yes, sir.
Okay. So now let us say the heat of formation of this compound is H1. The heat of formation of this compound is H2. The heat of formation of this compound is H3. The heat of formation of this compound is H4. And suppose I ask you, what is the delta H of this reaction? What is the energy change involved in this reaction? What should I do?
You add them, sir.
Yes. Which one do you add? Sir, I'll tell you. See, a simple example I told you. You find the energy of the products minus energy of the reactants. Correct or not? So here what do? You find the total energy, heat energy of the products minus you add all the energy of the reactants. Clear, ma? Okay. How do you add all the energy of the products? Tell me. What is H4? Formation of the compound D. Maybe I'll make it a little simpler for you by giving numbers. Well, everything is in variables, then you may have some challenge. Let's say this is 2, this is 3, this is 1. Let's say this is, okay, let's say this is 4. Okay. Now tell me, what is the, when I say H4 is the energy or enthalpy of formation of D. Then what is the energy associated with this, with 4D? Tell me, Enoch.
Repeat, sir.
Come on, full attention. Huh? The energy associated with the formation of the compound D is H4. Then what is the energy of 4D?
Oh. It will be 4H4.
That's all, right? That's all. Okay. Now, what are the, yes, Ranika, tell me, ma. What is the other product which is there with you in the equation? Looks like I'm waking up people.
1C.
1C is there. What does it mean? What do you mean by 1C? Is it some bus number?
No, sir.
What is
It's
1C?
one of the products.
Huh?
It's one of the products.
One of the product means I can simply say C, no? What is 1C? What is that one?
1 mole of C.
Very good. Tell me that way. You're a chemistry student, right? 1 mole of C, correct? Very good. So now, what is the heat? What is H3?
1 H3. Sir.
1 H3 we should do. What is H3? Tell me what is H3?
1 C. Sir.
H3 is, what is the meaning of H3?
It's like the heat released by one of the products.
Sorry?
Heat of one of the products.
Heat of formation of C. Okay? Heat of formation. So it will be, so I should add it or subtract it? Ranika, tell me.
You should add it.
Okay. 1 H3. Then what I should do? I should subtract the total heat of the reactants, right? Okay, I'll ask somebody else. Yes. Fuzail, come on, tell me, ma.
So 3H2 plus 2H.
3H2 plus
2H1.
That's all there. Okay, very good. So this will give me enthalpy of the reaction, ma. That's all. Okay. I would request another 5 minutes of time, guys. Let us do at least one numerical. Then I'll share this worksheet with you. You try the remaining ones. We shall discuss in our offline session. Okay. One numerical we will do and we'll conclude today's class. Okay, let us take up a problem. Okay. Heat of formations of carbon monoxide and carbon dioxide are minus 26.4 kilocalories and minus 94.94 kilocalories respectively. What would be the heat of combustion of carbon monoxide? There are two ways of doing it. Okay. First, I'll do your PU method of doing the sum. Okay. Heat of formation. Okay. When I say formation, students, all right. Let's directly look into the question first. Okay. Heat of combustion of carbon monoxide. So, which is one of the reactant you're very clear with? What is the reactant in this reaction? Come on, tell me. We need to find the heat of combustion of carbon monoxide. So tell me one of the reactants. What is my reactant here?
Carbon dioxide, sir.
Hey,
Carbon and oxygen.
I'm clearly saying heat of combustion of carbon monoxide. Heat of combustion of carbon monoxide. Which are you going to heat?
Carbon and
monoxide.
So carbon monoxide is a what? Reactant. Okay, good. Combustion. What does the word mean?
Burning with oxygen.
Very good. So what is my other reactant?
Oxygen.
Fantastic. That's all. Correct. Now I asked you the question for the answer you gave, Jerome. What is the product I'll get? Come on, go ahead. Carbon monoxide, if you heat it in oxygen, what will you get?
Carbon dioxide.
Exactly. Now your answer of carbon dioxide is correct. Okay, it's a product. So carbon dioxide is your product, right? And all these are gases, right? So the same first law of thermodynamics, we write it in a different way. We'll discuss that while we do the questions, okay? Like delta H is equal to delta E plus delta Ng RT. We will be discussing that probably in our offline class, okay? Now, CO plus. So is it a balanced equation? Hello?
No, sir.
No, right? So what do I need to do?
2CO and 2CO.
Okay, yes, correct, Enoch. So normally what we do is we do 2CO plus O2 is equal to 2CO. I mean, we'll just balance it that way, right?
Yes, sir.
But what we are going to do is, we don't want to change the number of moles. Is that clear, no? Number of moles. For example, when I say heat of combustion of carbon monoxide, it means heat of burning 1 mole of carbon monoxide. What is hidden here, which is not explicitly given?
1 mole of.
1 mole is not given. It won't be given. This definition implicitly says that it is, when I say heat of combustion, it means what? 1 mole of carbon monoxide. Okay, it's understood. So you should maintain this number as 1. Okay. So do that. To do that, you are going to multiply oxygens. The coefficient, stoichiometric coefficient will be half here. Is it clear to you? Very good. Very good. Now, come on, guys, tell me. We are going to get to the answer very quickly. I want the delta H for this reaction. And what is delta H here? Enthalpy change. Enthalpy change. What is it?
Summation P minus summation H.
Yes. So heat energy involved with formation of products minus heat energy involved with formation of reactants. That's it. So now tell me, what are all the products, guys? There is only one product. Why do you think?
Carbon dioxide.
Yes, carbon dioxide. So it's nothing but heat of formation of carbon dioxide. We represented as delta HF. Okay, carbon dioxide minus. How many reactants do we have? Yes, Enoch. Couldn't hear you.
2 reactants.
2 reactants. What are they?
Carbon monoxide and oxygen.
Yeah, now tell me, Ma. So it's 1 times the energy of formation of carbon monoxide.
Plus half times.
Very good, very good. Plus half mole of energy of formation of oxygen molecule. What is given in this question?
Only carbon monoxide and
Yeah, carbon dioxide
carbon
formation energy is given. Yes, that's minus 94, right? We can substitute that. Correct? Then what else is given for you? The energy of formation. Carbon monoxide is given. What is that value?
minus 26.
Minus 26.4 kilocalories given. But what is not given, Enoch?
Oxygen.
Oxygen is not given, and it will never be given. Because, take down the statement, any compound or element occurring in its naturally occurring state, the enthalpy of formation is 0. So oxygen occurs as what, no? In your natural, what is the natural state of oxygen? Is it nascent oxygen or O2?
Nascent oxygen.
No, nascent oxygen is not the naturally occurring form. What is the naturally occurring form?
O2, the molecule.
O2, right? Oxygen, when I say, it will be existing as O2 molecule. So when I say hydrogen, guys, hydrogen in its naturally occurring state, is it available as newborn hydrogen H atom or H2?
H2, sir.
H2, isn't it? What about nitrogen? Nitrogen gas, how is it available? N2, isn't it? What about your chlorine gas? How is it available?
Cl.
Yes. So, in its naturally occurring state, the enthalpy of formation is 0. Therefore, half into 0 is 0. So that concludes your answer. So what's your answer? Minus 94. Minus of minus is plus 26.4. So what do you get? Come on, tell me, ma. Yes or no? Correct. Minus 94 plus 26.4. How did you get plus? Minus of minus. So the correct answer for the question is second option. This is clear to you? Okay, when we meet in the class, I can tell you a shortcut, or I can give it to you right away. Okay, listen to this. This is called Hess's law of constant heat summation. This is how you will solve the problems very quickly with some logics. Okay. Say a carbon takes in what? Half oxygen molecule and becomes what? Carbon monoxide. And this guy takes in half oxygen molecule and then it becomes carbon dioxide. This guy takes in 1 mole of oxygen to become carbon dioxide. What is given in your question? Formation of carbon monoxide is given. What is our value? How much is the value? Minus 26.4. Formation of carbon dioxide is given. What is that value? Minus 94 is given. You are asked to find combustion of carbon monoxide, which is this is asked. That's all. This plus this will give you this. That's it. So X will be nothing but minus 94 minus 26.4. You can do it in no time at all. I will explain this once again in our class when we meet. Okay. But just note it down. Sums can be solved. This law is called Hess's law. What I did it here is called Hess's law of constant heat summation, which will be very helpful for you to do the sums very, very quickly. Okay. But anyways, for your PU, you will do it like this. Okay. Fine, students. Okay. Good to have all of you. All the best. Please prepare. The videos will be available to you today. So please go through the videos also and also the textbook. Right. Then we'll dedicate one session where we will be completing the last part, molecular orbital theory, in the next class. Plus, we will also do the remaining questions. I'm going to send you the questions. There are a few more questions. Please do attempt them. But anyways, we will solve it in the class also. Okay. All the best, students. With that, we conclude today's class. You all take care. Have a great day. Bio students, you will have to log in back in another 15-20 minutes. Okay. See you all. Take care. Good day. Bye.
Thank
Bye,
you, sir.
sir.
Thank you, sir.
Bye-bye.
Thank you, sir.
Bye.
Bye.
Bye, dear.